Now let's turn our attention to the topic of Java and Java applications. Before Java, most programming languages required a compiler that was platform aware. What was compiled was very efficient because it was compiled with specific platform instructions the compiler knew about. It was quite possible to have a common set of source stacks, but each platform required its own set of compiled modules. And that restricted application portability from platform to platform. A module compiled for one platform could not be run on another platform without recompilation. Java addressed this by hiding the underlying platform specifics from the program. It does this with a virtual machine for the execution of the Java program. We'll bring back onto the chart the platforms we showed before, and we'll note again how each has its own hardware and operating system characteristics. The objective was to shield the Java program from having to know about those hardware and operating system characteristics. The Java program is wrappered with a virtual machine environment. The virtual machine is a Java virtual machine, or JVM for short. The yellow bar that comes into the picture is the key. This is a layer of the Java architecture that provides what we call a layer of abstraction between the Java program and the underlying hardware. This abstraction is what hides the platform from the Java program. It does this by translating Java programming calls into the lower-level platform-specific calls. That means that Java for each platform has code for just that platform. That code is aware of the platform it runs on, and it is what translates a Java call into the specific call for that platform. Java is at the very heart of WebSphere Application Server. Java is a programming execution environment that provides a platform-neutral set of programming interfaces along with a platform-aware set of translation code to turn Java into the platform calls. IBM develops the Java runtime for each of its platforms. IBM abides by the standard Java specifications for the higher level of this architecture, and it develops the lower level of this architecture specifically for each of its platforms. Now we'll look a little closer at the Java code that runs. We'll discover that it is in fact compiled code, but this compiled code understands the JVM, not the underlying hardware. This compiled code is called the class file. We'll start by placing on the page a box representing the lower-level hardware, and we'll place a box representing the Java virtual machine. The developer writes the program using the Java programming language. The uncompiled source code typically has a file extension of Java. This source code is compiled to a class file. This class file is known as bytecode, which means it's compiled, but not compiled all the way down to the machine level. Think of it as a halfway state. By the way, Java compilation is done either with the Java C command or with the utilities of a programming tool such as IBM's Rational Application Developer. Now imagine something invokes the program. This in turn causes the Java program to turn to the JVM and make a program call. The JVM will read the invoked code line by line and run that code through an interpreter, which turns each Java call into the associated platform instruction call. As the Java program is called again and again, the interpreter translates the program line by line into the platform instructions. It's quite natural to see that previous illustration and wonder about Java performance. What we'll see next is how the Java runtime environment is capable of compiling the entire class file, so the interpreter is no longer needed. The just-in-time compiler, or JIT, as it is commonly known, will, after some number of interpreter calls for a class file, decide it's time to compile up the whole class. There are various algorithms at work here that seek to find the optimal moment to perform this JIT of the class file. JITting a class too early might result in wasted energy if that class file isn't used very often. JITting the file too late means that more interpreter calls are performed than was necessary. Somewhere between those two there's a balance, and that's where the algorithms provided by the Java runtime come into play, to find that balance for best performance. Then, when that Java class file is invoked, the interpreter is bypassed entirely, and the calls are instantly passed to the compiled machine-level code for execution. Now let's look at some of the program types associated with Java. First, we start out with what is increasingly true. That is, Java applications are developed using tooling environments like Eclipse or IBM's Rational Application Developer. You could write a Java program using a text editor like Notepad, but the more advanced the program becomes, the more likely the developer will use a development tool. Further, almost all Java applications used in WAS consist of multiple class files, not just one. The simplest form of Java program is the standalone Java class program. This typically consists of a single class file. These types of programs are not intended to be run in WAS, or more precisely, they don't run in WAS as a single class file. It is possible to wrapper them in some other class files, so they do run in WAS, but that's a topic beyond the scope of this video. The next category is Java Server Pages, or JSPs, and Java Servlets. These do run in WAS. In fact, these may be the most common form of program run in WAS today. They're considered web applications. In general, they are programs that render dynamic page content or provide navigation between different functional areas of a website. The final category we'll discuss here is the Enterprise Java Bean. These are typically used for more core business logic functionality. The use of EJBs is increasing. Quite often we see servlets and JSPs providing front-end web application function, with Enterprise Java Beans doing the more sophisticated function in the background. For WebSphere Application Server, our focus is on the two categories shown, JSPs and servlets, and Enterprise Java Beans. Let's provide a summary of the messages delivered. It's all about platform neutrality, and this is achieved by hosting applications within a Java Virtual Machine, or JVM for short. Lower-level function translates JVM calls to platform-specific calls. Java programs are compiled, so they're not like other interpretive languages such as Rex or shell scripts. The compiled code is called a class file, and it's compiled to what's known as bytecode. Bytecode is simply a fancy term for a Java program compiled for use in a JVM. Bytecode is interpreted line by line and turned into platform-specific machine calls. The just-in-time compiler, or JIT, is used to compile whole class files into platform-specific compiled code. But the JIT first determines how frequently a class file is used before it JITs the file. If every single class file were JITted, it would take a long time for each Java program to start. Rather than burn cycles JITting up seldom-used class files, the JIT uses sophisticated algorithms to determine when a class has reached the point of justifying the cycles to JIT the file. You may be thinking, why did we just go through all that? Isn't that too much detail for an essentials unit? Yes and no. It was critical we established Java at the heart of WebSphere Application Server. We did not want to assume everyone knows what Java is, and to those who might not have been familiar, saying Java is the heart of WAS would have been somewhat meaningless. It was important to establish how Java achieves platform neutrality. It does that through a layer of IBM-written code that understands Java above and the platform below. This concept is key because when we get to discussing WAS on ZOS, we'll see that the platform exploitation we will discuss takes place under this abstraction layer. Remember, WAS is WAS across all platforms, but WAS ZOS is different. That's not a paradox. It's all about platform awareness and exploitation below the Open Standard Interface line. We introduce the JIT because we understand it's a natural concern about performance when you see something described as line-by-line interpreting of code. Java does interpret line by line, but it also compiles into a platform-aware assembler module once a class file has been determined as justifying it.